In this lesson, we're going to add on to what we learned in photoelectric effect. In photoelectric effect, what we found was that when we struck a metal plate with UV light or visible light, when we shone a light on it, that an electron would be emitted, and that's the glowing light that we see. Compton upped the ante by using X-rays, and when he shone X-rays on a metal surface, he too also saw an electron being emitted, but what he noticed was that the refracting X-ray ended up being scattered. It wasn't a straight on, straight out, it was scattered. And that the scattered X-ray had an increase in wavelength. When we look at this formula where energy is equal to HF, when we increase frequency, we increase energy. And as we see our wavelengths change, we see the frequency vary, and that will have an effect on the energy. By having an effect on the energy, and also that we have an incident ray hitting a plate, and we see the electron go off in one direction, and we see the X-ray go off in another direction. Because we see the change in direction, we also know that we're going to see a conservation of momentum. So this is going all the way back to the first unit. This is the X-ray incident, and this is the X-ray scattered. So when we're looking at momentum, we always follow the conservation of momentum. And so the momentum before is going to be equal to the momentum after. Well, what we see before is just an incident X-ray, but what we see after is an electron being emitted and an X-ray being scattered. So we can say that the incident photon's momentum is equal to the scattered photon's momentum plus the electron that's been emitted, their momentum. And so because we're working at a molecular level, we're working with electrons. Remember that protons don't move, it's the electrons. Because we're working at a molecular level, these collisions, so when the X-ray collides with the plate, these collisions are elastic. And when we see elastic, we see conservation. Okay, momentum in is equal to momentum after. When we look at this, this is the diagram. So here is our incident X-ray coming in. Here's our plate. We'll put it right before. And we see the electron being emitted in one direction. And we see the scattered photon being sent in another direction. When we see a shorter wavelength, we know that we have greater frequency, we have more cycles in a given period of time. If we have a shorter wavelength, we will have an increase in frequency. When we have an increase in frequency, we see that we have more energy. Okay, going back to this formula here. When I have a longer wavelength, I have less cycles per second or per set time, and so longer wavelengths equal less energy because my frequency is decreased. Okay, we can show that photons have momentum, and Compton was able to do that with the evidence of the particle model of EMR, being that we are dealing with photons in packets of energy. So when we're talking about energy, we're talking about energy up here, we're talking about energy here. Not only are we looking at the conservation of momentum, but we're also looking at the conservation of energy. So whatever energy comes into the system, energy needs to be going out of the system. And so what is coming into the system? We have our incident X-ray. And then what is coming out of the system? This is our incident. This is what is coming out. We have the energy of the scattered ray. And we have the kinetic energy of the electron because it's in motion. This X-ray here, these two values here, we can look at energy of the X-ray being equal to Planck's constant, times the speed of light over wavelength, because we're made that connection here. If I have a shorter wavelength, I have a greater frequency, I have more energy. If I have a longer wavelength, I have less energy, I have less frequency. So we can say that these two, energy for the X-ray, can be determined this way. And then kinetic energy of the electron, because it's kinetic, the electron's been ejected, it's in motion. EK is going to be equal to 1/2 mv squared. Okay. Now, previously we looked at E in is equal to E out plus or minus work. But in this particular case, the work function is really small when we compare it to the other two energies. Because it's really small, we're able to just ignore it. All right. Since EMR has no rest mass, so what this means is that no time is an electron just sitting there waiting to be admitted. They're always in motion. Our way of learning to calculate momentum in the first unit was P is equal to mass times velocity. But because there is no P is equal to 0, we can't use this particular formula. So we had to derive a new way to calculate the momentum of a photon based on wavelength. And this is what was decided, that momentum is equal to Planck's constant divided by the wavelength. But the key takeaway here, aside from the formula, is this part here, that it needs to be in joules. So we've gotten away with using two different forms of energy. We've been able to use 6.63 times 10 to the negative 34 joules seconds, but we've also been able to use 4.14 times 10 to the negative 15 electron volts seconds. We can't do that anymore. Because we're dealing strictly in energies, we need to always make sure that we're in joules. And one of the things that we can look at is in all of the previous work that we've done with Planck's constant, where we've been allowed to flip and flop backwards and forwards, is if it just makes life easier, you can automatically convert an electron volt, right? 1 electron volt is equal to 1.6 times 10 to the negative 19 joules seconds. So we can make that conversion and then always just be dealing in joules. There's nothing wrong with that. All you need to know is that you can recognize Planck's constant can be one of two formats. So if we look at the formula for momentum, we notice that it supports the particle theory. It still has the idea of wavelength, and that's supported here by this wavelength piece here. And so this continues to support the wave-particle duality theory. EMR acts as both a wave and a particle simultaneously. So Compton was able to create a formula that could calculate the change in wavelength after it was directed at a metal surface. And this is what he came up with through all of his experiments that he was doing. Planck's constant is still a part of the equation, and now we're looking at mass over the, or multiplied by the speed of light. And then we multiply that whole piece by 1 minus the cos of theta. So again, Planck's constant has to be in 6.63 times 10 to the negative 34 joules. And theta is the angle here. This is the energy of the incident, and then we see the electron gets ejected, and we have the scattered X-ray. This is the angle here that they're talking about, not this angle or this angle. It's this angle here between the initial and the final wavelengths. So that's a key piece to remember. And then the one final equation that we look at is energy is equal to momentum times the speed of light. So again, energy needs to be in joules. Momentum is for a photon, and C being 3.0 times 10 to the 8. Let's put that into practice. Let's calculate the frequency of EMR whose photons have a momentum of 2.8 times 10 to the negative 27 kilograms meters per second each. So writing down what we know on the side, P is equal to 2.8 times 10 to the negative 27 kilograms meters per second. Again, these are units that we're familiar with. Because we're talking about a photon, we cannot use P is equal to mass times velocity. So we're going to look at using this formula to calculate frequency. When we're looking at this particular formula though, we see that we don't have wavelength over here. So in order to figure out wavelength, we can take the momentum that we do have, and we can use Planck's constant divided by wavelength to figure out wavelength. So wavelength will be equal to 6.63 times 10 to the negative 34 divided by momentum, which is 2.8 times 10 to the negative 27. And we should get a value of 2.36 times 10 to the negative 7 meters. Once we have our wavelength calculated out, then we can figure out our frequency by dividing velocity by our wavelength, and we get 3.0 times 10 to the 8 divided by 2.368 times 10 to the negative 7. Again, wavelength is measured in meters, and we end up with an answer of 1.2669 times 10 to the negative 15, 1 over seconds. If we did a unit analysis, we would have meters over meters by second. And so these meters would cancel out. This unit is hertz. So when we write it out to significant digits, we get 1.27 times 10 to the negative 15 hertz. Okay. Again, if a photon has an energy of 6.00 electron volts, what is the momentum of the photon? Well, we've just said that everything after photoelectric effect needs to be in joules, so we're going to multiply this by 1.6 times 10 to the negative 19 joules per electron volts, and we're going to get 9.6 times 10 to the negative 19 joules. Because we're talking about a photon and we've been provided energy and we're looking for momentum, that formula here is PC, and C we know to be 3.0 times 10 to the 8 meters per second. Looking for momentum, we can take our energy that we calculated and we can divide it by the speed of light. And momentum is equal to 3.2 times 10 to the negative 27 kilograms meters per second. When we look at unit analysis, we can see here in momentum that we have energy over the speed of light. Energy is kilograms meters squared per second squared. That's the unit for a joule, all divided by meters per second. This will cancel out that, and this will cancel out that, and you will be left with kilograms meters per second. So that's our unit analysis. Okay. When we're looking at an X-ray with a wavelength of 1.28 times 10 to the negative 12 meters, is shot at a piece of graphite. The X-ray is observed to have scattered at an angle, so it shot at a piece of graphite. The electron goes one way, the scattered wave goes the other direction, and this angle here, which doesn't represent it very well, is 15 degrees from the original path. Determine the wavelength of the scattered X-ray. This is the incident X-ray. This is the first problem. We know that the change in wavelength is equal to your wavelength final minus your wavelength initial. This part here, we see when we have the change in wavelength is equal to h over mc, all multiplied by 1 minus cos theta. Planck's constant has to be in joules. We're going to use the mass of an electron because those are what are emitted. Even though it's not stated anywhere here in the problem, an electron is what is being ejected from the plate. And we're going to use the speed of light as the constant. Okay, so when you're putting this into your calculator, you're going to do this math first, and then you will do this math. And you will see that your change in wavelength is equal to 8.27 times 10 to the negative 14 meters. From here, we can go back is equal to lambda final minus a lambda initial, or this is scattered and this is incident. And so we can see that 8.27 times 10 to the negative 14 is equal to our scattered ray, lambda scattered, minus 1.28 times 10 to the negative 12 meters. When I rearrange the formula, I will get the change plus the initial for a value of 1.36 times 10 to the negative 12 meters. The second part of the question is asking us to determine the energy gained by the ejected electron. So we can go back to this where we have the incident X-ray is equal to the scattered X-ray plus the kinetic energy of the electron. It's asking us to just determine the electron. So this we know from hc over lambda, as well as this. And then we are looking for kinetic energy. When we do the fancy math and we go hc over lambda incident minus hc over lambda scattered, it's going to be equal to our electron's kinetic energy. So we can write this all out, or what we can recognize is that we have hc multiplied by 1 over lambda initial minus 1 over lambda scattered is equal to EKE. All I've done is I've just pulled out the like term. Oops, this should be 1 over. All I've done is I've pulled out the like terms. So I'm going to go 6.63 times 10 to the negative 34 multiplied by the speed of light multiplied by 1 over 1.28 times 10 to the negative 12 minus 1 over 1.36 times 10 to the negative 12. And for my kinetic energy of my electron, I should be getting 9.43 times 10 to the negative 15 joules. Okay, last question in this series. An X-ray with a wavelength of 3.0 times 10 to the negative 12 meters is directed towards a piece of thin gold foil. So we've kind of seen something like this already when we talked about the gold foil experiment. So we have an electron or an X-ray that's hitting a thin gold foil. The initial X-ray is traveling east, so we're going to make this our positive, and strikes an electron initially at rest. So here's our electron sitting on the gold foil, waiting to be kicked out. And it's traveling, the ejected electron travels at 1.07 times 10 to the 8 meters per second to the east. What is the momentum of the scattered X-ray? This is the scattered X-ray here. Okay, so information that we have, because it's momentum, there's a vector. Both before and after is heading east. We're looking at the conservation of momentum. So we're going to have a before and an after. Remember how to set these up. What do we have before? We have our incident X-ray. And we have our electron that's just sitting there hanging out. Afterwards, we have a much longer scattered X-ray. And we have an electron that is actually moving east as well. Writing down the information that we have, the initial wavelength is 3.30 times 10 to the negative 12 meters. We know through momentum of a photon, we can do Planck's constant over a wavelength. And so we're going to have 6.63 times 10 to the negative 34 divided by 3.30 times 10 to the negative 12. P will be equal to 2.009 times 10 to the negative 22. For our electron, our velocity is 0 and our mass is 9.11 times 10 to the negative 31 kilograms. When P is equal to mass times velocity, we get a big old 0. Afterwards, this is what we're looking for. We're looking for P prime of the photon, and of the electron, we have, again, the mass is 9.11 times 10 to the negative 31, and our velocity after the fact is 1.07 times 10 to the 8 meters per second. So momentum being mass times velocity, we're going to get 9.75 times 10 to the negative 23 kilograms meters per second. So we can go momentum of the X-ray incident plus momentum of the electron is going to be equal to momentum of the X-ray scattered plus the momentum of the electron when it's been ejected. So we got 2.009 times 10 to the negative 22. It's asking us for this momentum here. Plus 0 is equal to P x scattered plus 9.75 times 10 to the negative 23 kilograms per meters per second. So Pxs is going to be equal to 2.009 times 10 to the negative 22 minus 9.75 times 10 to the negative 23. So our momentum of our scattered X-ray should be 1.03 times 10 to the negative 22 kilograms meters per second. Momentum is a vector, and it's heading east. Okay, you're going to stop here and you're going to work on these questions here, 4 to 7, 10, 12, 14, 15, and 20. And then to challenge yourself, you're going to work through practice problem number 2 through number 2 on page 277 and practice problems.